Welcome back to our videos on math. Today's topic relates to polynomial functions, and we'll be looking at these outcomes here. Mainly looking at polynomials other than just quadratics, looking to see if we can find something from the equation to give us a clue of what the graph will look like, and then starting to look at some characteristics. So to begin with, as I said, we've done lots of work with quadratic functions, ones that have x squareds in them. So we have done things like y equals x squared plus 5x plus 6, and we've looked at characteristics of that function. Today we're expanding that to include cubic and quartic and beyond. So we can look at polynomials of any degree. First off, here's a definition of polynomial functions. So functions have this form. So they have something x to the, say, 5th, and then it'll be x to the 4th, and then x cubed, x squared, x to the 1st, etc. And a, b, these coefficients have to be real numbers. So that's what a polynomial looks like. So let's begin talking about the leading term test. I know that when I had functions that looked like y equals, say, 2x plus 3, I looked at that and I thought, oh, that looks like it's of this form here. And I was able to get some information about this linear function right from the graph. We moved on to looking at quadratic ones, so here's that example again. And we could find some information from that. But this was the key part telling me it's a quadratic. So what we want to look at now is look at ones where, okay, if I have y equals x cubed plus 2x squared plus something else, when I see this, what kind of graph does it give me? I know this one gives me a straight line, this one gives me a parabola-shaped graph. So what does a cubic give me? And what does a quartic give me? What does a graph that's x to the 5th or x to the 7th give me? And are there some patterns that I can look at? Let's look at some. These are all graphs that I've drawn that are odd polynomials. Take a look at this one. Cubic, x to the 5th, x to the 7th. Doesn't matter what comes after. That might affect the shape a little bit, but it doesn't affect the general shape. So when I look at each of these, x to the 5th, x to the 7th, x to the 3rd, I notice that they all start from down here. So the graph starts from down here, and it goes up, comes down, and continues up. Let's look at this one. Starts down, ends up. Starts down, ends up. And certainly that's a characteristic of any odd polynomial function. It would start low and end high. Take a look at what happens when we change the sign of the coefficient of x cubed down here. Here I've changed the sign of the coefficient of each of those. And now take a look what happens. If I've changed the sign, I still have a general shape, sort of down, up, down, but this time I'm starting high and ending low. Starting high, ending low, high, low. So with any odd polynomial function, if I just sort of wanted to put that in terms, if my coefficient is greater than 0, I'm going to start low, and I'm going to end high. And when I say start and end, it's always referring to a left-right kind of movement. So this x cubed one, I know it has this kind of shape to it. Now, interestingly enough, I'll go back to the slide in a second, but this cube here actually tells me how many times this graph could cross the x-axis. May not cross that many, but that's its potential. Let me look back and just check that. Here's a cubed, here's the x-axis. 1, 2, 3. Notice this one, it's an x to the 5th graph. 1, 2, 3, 4, 5. An x to the 7th graph, it has a possibility of crossing the graph 7 times or less, as we'll see later. Okay, so going back to my review here. So if the coefficient's positive, I start low, end high. If the coefficient of the highest degree is negative, then I'm going to start high and end low. Start high, end low, like this. And this is a cubic, so it'll go like this. But if I had an x to the 7th graph, if it was a negative x to the 7th, it would start high and it would go down and do as many bumps as it usually does until I get a possible of 7 x-intercepts. We'll talk more about these bumps later. Now let's look at even polynomial functions. Here's a quadratic, our normal one. Notice it crosses. It has the potential of crossing twice. We know that sometimes I could have a quadratic like that that doesn't cross at all. But it has, at most, it can cross twice. A quartic graph, it crosses 1, 2, 3, 4 times. That one's a little small, but it has the possibility of crossing it 4. X to the 6th graph, crossing it 6 times. Same thing with their negative graphs. Notice it doesn't change how many times it could cross the axis. But let's look at the direction of opening. It looks like if it's an even polynomial graph, it can start high and it ends high. Starts high, ends high. Starts high, ends high. So if it's a positive coefficient of the highest degree, starts high, ends high. If the coefficient, however, is negative, sure enough, starts low, ends low. Let's just put that in here. So if the coefficient is positive, if the highest degree coefficient is positive, then the graph will start high and it'll also end high. Some people call that sort of a smiley face. Okay, it starts high, ends high, sort of like a smile. This one, if the coefficient's negative, then it's going to start low and do it however many bumps as it needs and comes down, ends low. So this one might be a frowny face. I don't know if it looks very frowny, but the idea with a negative coefficient of an even degree is that it will start low and it'll end low. Okay, so there we've sort of given us a little bit of a head start on that leading term test. So now let's start taking a look at some characteristics of graphs. With the quartic ones, we saw x-intercepts, we saw y-intercepts, we saw vertex, we saw axis of symmetry, we saw a minimum point, and there were lots of different characteristics that we found about a quadratic graph. When we look at other ones, a cubic, quartic, looks like this one is 1 to the 6th, there's other characteristics that we look at, maybe some of the same ones. In particular, the ones that I want to focus on are the x-intercepts, and those are the ones of most importance to us. So where does this thing cross or just touch the x-axis? I can also talk about a y-intercept, but the ones that I'm mostly concerned with are the x-intercepts. We can also refer to things like a relative minimum, or we could talk about here sort of a relative maximum, sort of where there's a vertex-like point. But that's not the focus. My focus is on these x-intercepts. And the rest of this section will be finding ways of determining what those x-intercepts are. Okay, so in finding x-intercepts, or zeros, or solutions, or roots, a lot of those words are thrown around interchangeably. In order to solve for those, we need some strategies. First off, when I had a quadratic, I could simply take that and I could factor it. So this would be x minus 3, x minus 2. Solving for 0, I use the zero product rule that tells me that x could be equal to 3 or x could be equal to 2. Those are my two zeros. Those are my two x-intercepts, two roots of the equation, and also two solutions to this equation here. When I get a cubic, what do? Like, I had strategies here. I could factor it. I also had that quadratic formula, minus b plus or minus, you know the one. Those are tools that I could use to solve this kind of an equation. When I have a cubic, different story. I need different tricks. We'll see a few here in this section, but we'll also see some in future sections. So for example, this one, when I look at it, I'm thinking, well, it's a cubic. We did some grouping. Let's see if grouping will work. So maybe I'll factor out an x squared out of these first two. And what does that give me? X minus 2. And I'll factor a 3 out of this one. That leaves me with an x minus 2. Oh, common. As long as they're common, I can do this then. So I can factor out an x minus 2, and I'm left with x squared plus 3. So I could factor by grouping, then equate this to 0 to solve the equation. So x minus 2 is equal to 0, or x is equal to 2, and the other equation I'd get is x squared plus 3 is equal to 0. To solve this, I'd move the 3 to the other side, and then I'd look at it and say, there's no way I can get a number here that when I square it gives me a negative number. So there's no solutions from this part of the equation. So my only solution for this equation would be 2. So those are doing some things that we've done in the past, but we need some other strategies because I'm not always going to get a beautiful one that will be able to factor by grouping. So one of the ways that you can do is just willy-nilly pick a number. And you can say, well, what is the value of the function when I plug a 2 in for x? And if I plug a 2 in for x, if I come out to 0 when I plug that in, then that means that the number 2 is a 0 or is an x-intercept. And following that logic, sort of going back to one of the examples we did before, if 2 is a 0, then x minus 2 would be a factor of that particular polynomial. So here's a quick question. Is minus 2 a 0 for this function? Okay, well let's try it. F of x is equal to, let's plug in a minus 2 everywhere I see an x. Minus 9 minus 2 squared plus 14 times minus 2 plus 24. I want to see if I get a 0 out of this. Minus 2 cubed is minus 8. Minus 2 squared is 4 times minus 9 is a minus 36. 14 times minus 2 is a minus 28 plus 24. Okay, so I want to see if when I plug in a minus 2, I get 0. Minus 8 minus 36 is minus 44. Minus 28, that'd be like minus 72 or something. There's no way I'm getting a 0 out of that. Therefore, I would say minus 2 is not a 0. Nor is it an x-intercept. Nor is x plus 2 a factor. So that's one way I could determine some zeros, just by plugging in a number. But you think to yourself, well, you know that for a number like 24, I could plug in 1 and 2 and 3 and 4, probably all factors of 24. That would be a whole lot of work to try and do that. So we have some other solutions, and we'll see those in another video. Okay, just one other little thing that we need to talk about when we get into larger polynomials, and that's the idea of even and odd multiplicity. Sometimes you will have graphs that when you factor them out, and we'll see how to factor them in the next section, but when you factor them out, you get a factor where you have 2 of them. So I have x plus 2 and x minus 2 squared, so I have 2 of these factors. Whenever I have an even multiplicity, what happens to the graph is it comes and just touches at that point but doesn't go through. So the graph is tangent to that point. Touches but does not go through. If I have an odd multiplicity, where when I factor some kind of polynomial I get 3 or 5 or 7 identical factors, then what happens at that point, so the factors x minus 2, the 0 would be a positive 2. So at positive 2 here, notice what happens. That it comes and sort of bends, but then continues through the point. Even, the graph just touches. odd, it goes through. So it goes through the axis at that point. So if I'm taking a look at to graph a polynomial, then I'm supposed to graph this polynomial. Currently, I don't have a whole lot of strategies to determine zeros. This one I might be able to, but I don't have lots of strategies. First thing I would look at and say, okay, it's a third degree polynomial. When we did those, they had this sort of bump shape to them. Either this way or it was that way. One of the two. It's negative. If I think back to it, it's not this one, it's this one. So I sort of know what the graph's going to look like. It's going to look like that. It's a cubic. It has that one start high, end low, and a little bump in the middle. Now, to be more specific, I want to know where that crosses the x-axis. Well, I need to factor this. Well, I guess I can see that I could factor out a negative x squared. I'd be left with just an x here. Here, I think I'd be left with a positive 4. So here I've got x squared, so that's one of the factors, x squared, multiplicity of 2, and x plus 4. So if I equate this instead of to f of x, if I equate this to 0 and solve, I can determine what the x-intercepts are. So here I can say that since there's a product, I've got x is equal to 0, or there's another x, right, x squared, so another x is equal to 0. Or x plus 4 is equal to 0. So these are both solved, and this one would be x is equal to minus 4. So here I have 3 solutions, or 3 zeros, 3 solutions of this equation. When I look at it as a function, there are 3 x-intercepts. So it's 0, 0, and minus 4. Now when we are talking about multiplicity, we said if it's 2, it just touches. So let's try and draw this graph. I know something funny is happening here at 0, and something funny is happening at minus 4. It's supposed to look like this one, coming from above, coming down. So let's see if we can do that. It comes down, comes through this point, comes back up. Multiplicity is even, so it just comes up to this point and bounces back down. So that's generally how that cubic function would look. Now lastly, the intermediate value theorem. This one is sort of handy. I don't use it a whole lot, but it is fairly handy. And it basically says if I plug a value in for x and the resulting value is positive, then I plug in a value, say, of 3, and if I get a negative value when I plug that in, since one's positive and one's negative, in between 2 and 3, there must be a crossing of the x-axis. So it's a way sort of narrowing down where those x-intercepts are. We'll see better tools in the future how to find these out, but let's just finish this one. So let's see what f of 2 is. So I put a 1 and a 2 down here. Well, let's leave a 2 there and we'll put a 1 there. Okay, so plug in a 1. 1 cubed plus 3 times 1 squared is 3, minus 9 times 1 is minus 9, minus 13. So this is 1 plus 3 is 4, minus 9 is minus 5, minus 18 is, or minus 13 is minus 18. So when I plug a 1 in, I get a minus number. Let's see what happens when I put in a 2. 2 cubes 8, 2 squared is 4, times 3 is 12, minus 9 times 2 is 18, minus 13. Add them up. 20 minus 18 is 2. 2 take away 13 is a negative 11. So since both of these are negative, I would assume then that there's no x-intercepts between 1 and 2. Because they're both negative, it's still on the same side. Let's try, just for example, 4. Let's see what happens with 4. 4 cubed, 64. 4 squared, 16, times 3 is 48. Minus 9 times 4 is 36, minus 13. You'll see here that I'm going to be getting a positive number. I'm not going to figure out what that is, but it'll be positive, indicating to me that somewhere between 2 and 4 there is a crossing of the x-axis, an x-intercept. That's what's known as the intermediate value theorem. So today we've just briefly had an introduction to polynomials. We've looked at things like leading term test to see what kind of polynomial I have. And then at the end we've just done some introductory ways of finding zeros or x-intercepts of polynomials. In the future we'll look at some more rigorous ways of finding exactly what those x-intercepts are.